Is an introduction to motion in general. There are some aspects of motion that you're going to already be familiar with, but there are a few pieces of terminology that are probably not something you're used to using. When we talk about physics and we talk about motion, we talk about two different quantities. One quantity is a scalar. The other is a vector. The difference between them. A scalar is just a number. It's a magnitude. So, for example, I live 15 miles from here. That's a scalar. It doesn't tell you a whole lot other than I live 15 miles somewhere away from here. But it's not complete. It doesn't give you a very good idea of where I live. A vector is something that has a magnitude and a direction. So telling you I live 15 miles north of here gives you a much better idea of where my house might be. So a vector has a magnitude and a direction. Some quantities we talk about in physics are just scalars. Mass, for example. Height would be a scalar. Time is a scalar. It doesn't have a direction. It doesn't mean anything to say 4 seconds that way. 4 seconds is 4 seconds. A vector is something that needs a little more clarification. Needs not only the magnitude, but also a direction to move in. So some examples. A scalar. How far? So a distance. That's an example of a scalar. The vector corollary would be the position or a displacement. Position, meaning 15 miles north of here. How far and what direction. Displacement is where you end up relative to where you started. Okay? For both distance, position, and displacement, for all of these, the symbols we're going to use, maybe an X, generally correlating to the horizontal or x-coordinate system. A Y, if we talk vertical. You may see an S or an R as well. Any of those can mean distance or how far. We still use X, Y, S, and R for position as well. So we need a way to distinguish whether we mean how far or position, how far and what direction. To represent a vector, we draw a little arrow above it. So in the book, you're going to see this as well. A letter with a little half arrow above it means it's a vector. To accurately express a vector, you need a number, a magnitude, you need a direction. So 15 miles north would be a vector. 15 miles north. Okay. Displacement, by the way, is specifically a change in any of these. A change in position. You've probably seen delta before. Delta, remember, always means your final value minus your initial value. So displacement is just looking at where you end up relative to where you started. Position is measured relative to one set place, an origin. You have to have a set origin for your problem. So, for example, when I'm saying I live 15 miles north of here, where's my origin?
Here.
Here. Exactly, I'm measuring from here. So, position, you have to have a set origin. You can choose your origin for your problem, but you have to have a set origin. Displacement just tells us where they are relative to where they started. Some other quantities that we're going to use. Speed. Speed is simply how fast are you going. Your speedometer will tell you that. That's when you look. If you pass a cop, you look really fast to see if you're going too fast. Now, in the news, in our normal everyday life, we've tended to use speed and velocity interchangeably, but they really aren't. Speed is simply how fast. It's a scalar only. It doesn't tell us anything other than how fast are we going. Velocity is how fast and what direction. So, speed and direction. So the magnitude is the speed, that's the number. The direction is in what way are you traveling. Both are very important in different problems. Symbol. We use a V to represent speed. We use a V to represent velocity. So how am I going to know the difference?
Arrow.
Fabulous. Arrow above it. Fantastic. So speed and velocity are different in terms of the direction. Okay? So they both represent how fast. Velocity just includes the information of in what direction as well. The other term we're going to use with motion is acceleration. By definition, acceleration is a change in velocity. We don't have a separate term that we use for the scalar value of it versus the vector value of it. We can talk about just the magnitude of acceleration, or we can talk about the actual acceleration in terms of how much and what direction. Okay, so we can talk both ways. Keep in mind, this is a tricky one for people. By definition, acceleration is a change in velocity. So speeding up, that is one way to have an acceleration. If you are speeding up, you have an acceleration. If you are slowing down, you have an acceleration. I know it sounds kind of funny. Usually we say deceleration, but the term acceleration still applies. But how else can you have an acceleration? Change your direction, turn. Exactly right. So you could be traveling at a constant speed, but turning, and you will be changing your velocity. That means you have an acceleration. Okay, so if your direction is changing, that is another way to have an acceleration. Okay, so in terms of vectors, when we talk about vectors, number one, we generally have a coordinate system. So let's say we have a coordinate system, and I'm putting home base right there. So the marker is home base. In order to talk about the position of an object, you have to have a home base. You have to have an origin. If you don't have an origin, position doesn't mean anything. Okay? So if I'm on this side of home base, then my position is positive, and however far that happens to be. You okay with that? So a negative position would be if I'm on this side of home base. So we're looking at the traditional Cartesian coordinate system. If I'm over here anywhere, I'm positive. If I'm over here anywhere, my position's negative. What if we're talking about a ball? Throwing a ball up in the air. If it's above the origin, call it positive. If it's below the origin, we call it negative. Okay. Velocity. Let's say I'm over here, and I'm walking this way. Is my velocity positive or negative? Positive. If you draw the arrow representing the direction I'm walking, it's pointed in the positive direction. So my velocity is positive as long as I'm headed that way. It doesn't matter where I am. Even if I'm on the negative side, but walking in the positive direction, my velocity is positive. You okay with that? If I'm walking in the negative direction, my velocity is negative, regardless of where I am. If I'm headed that way, then my velocity is negative. If I'm headed that way, my velocity is positive. Okay? Okay, here's the harder one. Let's say I'm headed that way and speeding up. So I'm going this way and I'm walking faster and faster and faster. What direction is my acceleration in? Positive. What if I'm walking that way still, but slowing down? Then my acceleration is negative. Acceleration. The direction of the acceleration depends upon the direction of the velocity. If your velocity is positive and you're speeding up, your acceleration will also be positive. What if my velocity is negative and I'm speeding up? My acceleration is negative. I know that seems really counterintuitive. Negative acceleration does not necessarily mean slowing down. If my velocity is negative and I'm speeding up, then my acceleration also has to be negative. If the acceleration is in the same direction as the velocity, you're speeding up. If your acceleration is opposite in direction to the velocity, you're slowing down. So if we're headed this way but slowing down, my acceleration is positive. That's a little counterintuitive. You kind of have to accept it at first.
So I'm trying to piece this together. Is velocity always going to be standalone vector?
Yes.
Okay, so if it's a standalone vector, is it going to have two values? One value is speed and one value is direction?
Generally, when we talk about a vector, the length of... So if we were to draw a vector to represent velocity, the length of the vector would be the speed, how fast. And then the direction it points is the direction of the vector.
So for example, you'd have a vector like this, and it's positive 5 speed and positive 5 direction, or...
No, so if we had, say, like this, if it was a 5?
No, I'm the actual vector itself, would it be, bracket 5, comma 5?
No. We could write it in terms of, say, if it was 5 meters per second, for example, but this side was 4 and this side was 3.
Okay.
We could write it as a 4, comma 3. We have to break our vectors. If they're not straight along the horizontal or vertical axis, we have to break them into their, what we call components. So we have to break it into the pieces that do lie along the x-axis and do lie along the y-axis.
But
we'll do more with that later.
okay.
Right now, our problems are going to lie cleanly on a straight line. So they're going to be all on the x-axis, all on the y-axis. They could be on an incline, but they're still going to be straight. So that we don't have to worry about breaking them down quite yet. Okay? But at any rate, the length of it still represents whatever the speed is. The direction, whichever way you draw the arrow, represents the direction.
But for now, that only matters if it's positive and negative.
Correct. Exactly right. So only thing that matters right now is getting the correct positive or negative sign on it. Let's say we have a graph of our position as a function of time. So this point right here represents our origin, wherever we've chosen our home base to be. The graph looks like that. What can you tell me about our motion? We're just sitting in one place, standing in one place. We're not moving. We're constantly at the exact same position. We haven't gone anywhere. We haven't moved towards or away from our origin. So our velocity is 0. Our velocity is constantly 0. So what's our acceleration? Also 0, because the velocity is not changing from the fact that it's 0. What would this represent? Where are we starting? Positive or negative? Negative. So maybe somewhere over here. We're not worried about the actual numbers. What's happening? We're starting negative, but then what? We're moving positive. So, moving straight across. I heard something about velocity. Constant velocity. Why do you know that? Because it's a nice, beautiful straight line. Exactly right. In this case, our average velocity would be the same as our instantaneous velocity at any point in time. Well, at any point during this motion, at least. If the velocity is not changing, then average overall is the same as the instantaneous at any one point. You have that? Average velocity is simply our change in position over our change in time. Where we ended versus where we started, and how long did it take for it to happen. Let's do something like that. So where are we starting? Origin, so home plate. We're walking in what direction? Positive. At first we don't walk very far, so what can you say about our velocity? Slow, small, but it gets bigger and bigger and bigger because we start covering bigger and bigger distances. At this instant, what's happening? We're turning around. Because we're going to head back. We're going to come back to home base. So this is moving to the right and coming back. But it's moving to the right where we're speeding up, slowing down, turning around, coming back, speeding up, slowing down until we get back to where we started. What's the average velocity? Sorry, go ahead.
I had a question. So the time when you got to that point and you started heading back the other direction, that would be like the peak of your graph there?
Uh-huh. Exactly. So this is the turnaround point. What is the average velocity for this particular trip? It's 0. Exactly right. Delta x is final position. Our final position is back at 0, minus initial position, which was 0. So our change in position is 0. Our average velocity is 0. That's because we headed that way for half the time, and then we were headed that way for half the time. It averaged itself out to be 0. Doesn't mean nothing happened. That can be a little counterintuitive. Average velocity of 0 doesn't mean there was no motion. It just means there was equal amounts of motion, positive direction, to cancel out the motion in the negative direction. What would the average speed be? What information would we need to know to find the average speed? We just need to know how far that was, total distance, measure how many meters it was there and back. So average speed is just the total distance. It doesn't matter the direction over the total time. So the average speed would not be 0, but the average velocity is 0 because we ended up where we started. Now, if I were to tell you that my average speed on the way to work is about 50 miles per hour. I don't really know what it is, I'm guessing. Does that mean I'm a slowpoke? Am I the person in the fast lane that you're getting mad at because I'm going so stinking slow? Not at all. Why?
Because you have freeway speed and then you have street speed. speed and you're averaging both.
Exactly
You're
right.
sitting at stoplights.
I have stoplights to sit at, I have stop signs to sit at, so I have a period of time when I'm not moving at all. Streets, I drive slow on. Freeways, I drive fast on. Once you average out all the values, 50 miles per hour works. There's periods of time when I'm not moving at all. You have to take that into consideration. So average speed doesn't really tell you a whole lot. If you're driving down the freeway, I usually go about 80. Don't know if I should admit that, but I do. When you're driving down the freeway and you notice the cop car sitting there watching you, do you care what the average speed is? No. You want to know the instantaneous value. That one's easy to get. Look at your speedometer. There you go. You got your instantaneous speed. Assuming your speedometer is reading correctly. Okay, instantaneous velocity. That's another thing. Now, if you have a speedometer and a compass in your car, I suppose you could get it. Because your speedometer will tell you how fast and your compass will tell you what direction. That's good enough. Let's go back to this example though. Average speed is simply taking, average velocity is simply taking a final position minus initial position and divided by change in time. What if we wanted the average speed for the first half of the motion? The final position would be here. This was the initial position. So this would be our delta x. This would be our delta t. When we take delta x over delta t, we're simply finding the slope of the line that connects those 2 points. So the average velocity for the first half of the trip would be positive. It's bigger than the original speeds we were going. It's smaller than the middle speeds we were traveling at. And it's bigger than the final speeds. How do we find instantaneous values? So we want to find the slope of the line that's tangent to the graph at the instant we're looking at. So we have a tiny little delta x and a tiny little delta t. Taking the limit as delta t goes to 0 of delta x over delta t. So we're finding a very small time frame, which gives us a relatively small delta x, which is the derivative of the position with respect to time. So mathematically, if we want to find the instantaneous velocity, we need to have the function that describes the motion so that we can take the derivative of it. Or it needs to be one that we can find the slope from the picture. So the instantaneous velocity, the velocity at any instant in time, is equal to the derivative of the position that describes the motion. The instantaneous acceleration is simply the derivative of the velocity with respect to time. You can work backwards as well. If you have an equation that describes the acceleration, you can integrate and get the equation that describes velocity. So we can go up. Velocity would be the integral of the acceleration. And likewise, position would be the integral of the velocity. So we're going to be using these calculus relationships a little bit in terms of solving for instantaneous values. In general, it's the instantaneous values that we're interested in. Averages on a whole for motion aren't as important usually. It's usually the instantaneous that we want. Okay?